Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to Optimization in Civil Engineering. In the last lecture, we discussed about the pattern search methods. And in the pattern search methods, we discussed about the hook-Gibbs method and Powell's conjugate direction method. In the both methods, no doubt we could reach the optimum solution faster than the other methods for the multivariable objective optimization problem we have discussed earlier, which were random search method, grid search method, and univariate method. Once we identify the pattern, we could reach the optimum solution faster. But still we are not using or we are not considering the gradient. If you recall from your single objective optimization problem solution, or even in the classical method of multivariable objective optimization problem, we clearly showed that if we understand the gradient, we can reach closer to the, or we can reach to the optimum solution sooner. Today we are going to discuss about the gradient based method which can be used in solving the multivariable optimization problem. The gradient based method, we have already discussed about it in the classical methods of optimization problem solutions for the multivariable objective function as well. However, today we are going to discuss about the numerical methods which can be employed to solve the multivariable optimization problem using the gradient information. If you recall, the numerical methods that are employed in unconstrained multivariable optimization problem can be divided into broadly two categories. One is direct search method and the second one is gradient based methods. We have already discussed the various methods related to the direct search method. Today we are going to discuss about the gradient based methods. Within the gradient based methods, the four major methods which are there are Cauchy's method, Newton's method, quasi-Newton's method, and Marquard's method. Among the four, today we are going to discuss about Cauchy's method, Newton's method, and Marquard's method. We are not going to discuss the quasi-Newton method in this class. So to start with the gradient based method, we have to understand the limitations of the other method and the benefit of this particular method or the gradient based method. If you look into the previous direct search method, you realize that the number of objective function evaluation required in those methods are very high. In random search method and the grid search method, we hardly use the trend or direction towards which the objective function was getting better. In random walk method with direct exploitation, in univariate method and pattern search methods, we tried to use the trend or direction in that help to improve the objective function value. However, these methods used certain number of objective function evaluation to decide the direction. Now, this number of objective function evaluation to decide the direction or the pattern can be reduced if we know the gradient of the objective function at a particular location. So for this reason, the gradient based methods require less number of objective function evaluation. However, in order to obtain the gradient, we need to have the first order or sometimes the second order derivative of the objective function. And this could be sometimes a concern for real world engineering problem. So if those concerns are there, if we cannot estimate the first order and second order derivative of the objective function, then we would rather stick to the direct search method. by any chance, if we can do that, then we would like to prefer the gradient based method. So within the gradient based method, we said that we are going to discuss the three methods. So let's start with the first method, which is Cauchy's method. It uses the steepest descent direction. So if you are looking into the objective function value, it is going to give us the gradient on the surface at the point where we are evaluating. For example, in this particular objective function, if we are looking into a point here and looking into the surface, if we try to find out the gradient, it may give us something like this. And if we try to move along this gradient, particularly if it is a minimization problem, we are going to go towards the negative gradient or towards the gradient where it is reducing. So if you are going towards this direction or the negative direction of the gradient, if you are going in this direction, then we'll reach to a point where the objective function is minimum for this particular direction. Now whichever point we reach, from there again we can search the gradient and again try to go towards the minimum point, and if we keep on doing that, eventually we'll reach the minimum point. Likewise, if we go to the other direction, which means the gradient is increasing or ascending, so which is going to be this direction, we can reach to the maximum point or solution which is going to, or location which is going to yield the maximum solution objective function value. So with this concept, let us look into the algorithm. So in this algorithm, in the very first step, we are setting the counter as 0, and then we are choosing a start point xi, a sufficiently small precision value epsilon to ensure that we can terminate our algorithm. Then once we know that point, we need to find out the gradient at that particular point. For this reason, we are doing the first order derivative at that particular point in the second step. Once we find out the gradient, it is going to be a vector because we have more than one variable. So this vector, once we look into the scalar quantity of that, and if we find that the scalar quantity of that vector, direction vector or the first order derivative vector, is greater than the precision which we have set, then we need to perform a unidirection search from the point where we started along the direction of the gradient. This search is going to lead us to the optimum point, which is going to be our next point, and this optimum point objective function value can be represented as this way. And if we try to solve this particular equation, we can optimize the lambda value, and once we optimize the lambda value, we'll get the new point, and once we get the new point, we move to the step 4. Otherwise, if we find that the scalar quantity of the direction vector is smaller than the precision, we are going to terminate the algorithm and report the point which we have obtained so far as the optimum point, and the function value at that point as the optimum function value. So in the step 4, once we found out a new point, we need to ensure that the new point with respect to the previous point is relatively far off. This check is going to help us to understand that we are not generating points in the close proximity of the already obtained solution. So once we do that, and if we find these 2 points are far off, which means in this case we are using the same precision value, and if this happens to be greater than that precision value, then we are going to set the I counter or increase the counter by 1, and again we go to the step 3 where we are going to find out the gradient and move along that direction. In case if the points are very close, then again that leads us to the termination of the algorithm and report the finally obtained point as the optimum point and the objective function value at that point as the optimum function value. Now in this particular equation you see that we have used plus or minus. It means that if we want to minimize the objective function value, we should use the negative of the gradient, and if we want to maximize, then we need to use the positive gradient. So this same algorithm can be used for the minimization or maximization by changing this particular sign to negative or positive. Let us look into this algorithm through an example. We have chosen this example. It's the same example which we are using for the last few algorithms. We have chosen the start point as 0, 0 and the precision value as 0.5. Now at the point 0, 0, we can find the gradient, and it is going to be negative 14 and negative 22. At this point, the scalar quantity of the gradient is going to be 26.08, and this is more than the precision which we have set, so we need to search the better point along this particular gradient or along this particular direction. So for that purpose we set up the new point, and this is a minimization problem, so we are indicating it as negative lambda 0 and the gradient. Once we do that, the new point is expected to be like this, and if we replace this point in our objective function and optimize the objective function, that is we are going to maximize the lambda 0 value, then we can see that the lambda 0 value is going to be 0.127, and using this particular value in the equation of x1, replacing it, we can obtain the actual x1 value, which is going to be this. At this point, if we see how far this point has moved from the previous point, which is x0, we'll find that the ratio is going to be infinite, which means it is quite a movement, and we can look for the next iteration. So in the next iteration, based on the new point, if we find out the gradient, we can obtain this particular gradient, and the scalar quantity of that gradient is going to be this. Again, this value is more than the precision which we have set, so we can search for the new point along this gradient direction, and once we do that, we need to write it in this format, and the point is going to be this. As we replace this particular point in our objective function and try to optimize the lambda 1 value, we can get the lambda 1 value as 0.0397. So our x2 point is going to be 3.01 and 1.999. At this point, if we try to compare with the previous point, we'll see that the relative movement of the point is actually 0.44, which is less than the precision which we have set. Now in this case, we have the same precision value for the point as well as the gradient. We might as well like to have two different values for those two factors. It all depends on the objective function and how sensitive is our variable or the design variable positions are. So since it has reached the termination criteria, or it has met the termination criteria, so we are terminating the algorithm, uh, terminating the process and reporting the optimum point as 3.01, 1.99, and the optimum objective function value is going to be 0.018. Let us look into the graphical representation of the solution, how it followed through. So we started from the point 0, 0, and once we estimated the gradient, it indicated the gradient is going to be this direction, and if we choose the negative gradient, it is going to be in this particular direction. And in this particular direction, if we want to maximize or move to a point where the objective function is going to be the minimum, then we will be reaching this particular point. This is point is 1.79, 2.81. Now from this particular point, again if we estimate the gradient, we'll find that the gradient is indicating this direction, and again if we choose the negative gradient because we want to minimize, then we can reach to the point this, which is our final point, 3.01, 1.999. And once we reach this particular point, if we compare the relative movement of this point with respect to the previous point, we'll find that it has met the termination criteria, and hence we have stopped. If we had chosen a higher precision or a better precision for this movement, we might have to go for one more step or couple of more steps to fine-tune our final result. So this was about the Cauchy method. Next we'll be discussing about the Newton's method. We have already discussed about the Newton's Raphson method for the single variable optimization problem. The Newton's method for the multivariable optimization problem is also similar. In this case, we do use the second order derivative for the direction, and this helps to reach the optimum solution even faster. So in the Newton-Raphson method, we had used the first order derivative divided by the second order derivative to set the direction. In this case, we are doing the same thing. However, the second order derivative is going to yield a Hessian matrix. So that Hessian matrix, inverse of that, multiplied by the gradient vector, is going to give us the direction. And again, like the Cauchy method, we are going to use the negative direction if we want to minimize our objective function. If we want to maximize your objective function, then we are going to use the positive direction. So the method is going to be exactly same as the Cauchy method, except in the step 3 where we had selected a particular direction and reached to the maximum point using that direction, we are going to change the equation for that. In this Newton's method, we are going to use this. So in the Cauchy method, we did not have this particular term. In the Newton's method, we do have this particular term. So let us look into the same problem. If we are trying to use the Newton's method, we have this objective function value, and this time we are starting from a different point, which is 2, 1. We have same precision value 0.5. Now at this particular point, if we find out the gradient, we'll find that to be this, and this gradient, the scalar quantity is 62.61, which is very high compared to the precision which we have set. So we are estimating the Hessian matrix or the second order derivative of that